So who am I? I'm a physicist. I'm a STEM educator. So what I do for my full-time job, and it's something that I've been doing for almost a decade now, from my undergraduate career to now, is that I visualize physics concepts for students using different machines, different kinds of equipment, and I'll show you exactly what that means in the next slide. But my role is more of an educator role than a hard scientist role, and so I really care about how scientific content is presented to people. I think it's important to not just regurgitate things or not just show people things, but to really immerse them in the concept, to really have them understand what it means in the context of the real world, because that's what physical science is all about. It has implications in the real world. And that's not just physics, it's also chemistry and biology, but those aren't my content domains. Now, I'm also a education researcher, which means that I'm interested in how people think and how people learn. And this is more of an intersection between cognitive science and psychology, as much as it is about the performance side of things and just, how are we representing information. This is a picture of that team. And I am a physics subject matter expert for them, or well, I was, and then I turned into kind of the researcher developer role that I discussed. But here you can see, actually, this isn't everyone, but we've got UI, UX designers, we've got psychology and cognitive science students, we've got people doing machine learning, doing C sharp, and so it's a very diverse group of people. And this lab is very focused on embodiment. And so Mina Johnson Glenberg, she leads this lab, and she kind of as a bedrock for all of our research, there's these necessary 9 principles that we should consider, or that she proposes that we should consider when designing games for STEM education. And we kind of measure efficacy and cognitive change in STEM education and STEM students using these principles, right? So I'll just read them off real quick. We want to scaffold cognitive effort, which means that you introduce things one step at a time. You want to use guided exploration to have the user explore that scaffolding. You want to give immediate and actionable feedback, and so that's goes hand in hand with assessment. You want to play test very often with the correct group, the end users. You want to build in opportunities for reflection. This next one's really important. You want to use hand controls or gestures for active body-based learning. And I'll talk about that a little bit more in a second. And you also want to integrate these gestures in a way that maps to the content to be learned. And they need to be worth the time and extra expense. They have to promote learning. And so, like, for example, you don't want gestures that have nothing to do with the content that you're learning. That's a surefire way to make sure that a memory is not made and doesn't map the agency well to the user's brain. And so the last one is you want to embed gesture as this form of assessment, both during and after the lesson. And I'm going to go back one slide real quick. This is what I do for my main job. Before I get into the games, I have to talk about physics a little bit because, like I said, it's very near and dear to my heart. In the top left here, you can see that I'm doing what's called a tablecloth pull, and maybe you've seen it as like a magic trick, but it's an example of Newton's first law. And when basically, if you pull the tablecloth slow, the plates will move along with the tablecloth. But if you move it fast, because the plates have inertia, they don't move at all. And this is like a really flashy demonstration. It creates, like I said, that memory for people. In the top right, that's I'm showing how an electric guitar pickup works. So when you move a string around a magnet, it creates that wave signal that you can put into a speaker and hear as sound. In the bottom left, I'm using a gyroscope to spin myself on a chair without doing anything like pushing or pulling. I'm just kind of rotating this spinning wheel. And that's a really counterintuitive thing for a lot of people. But when people do these things, and I don't just show them, I let the students do these things, it really creates that strong learning signal, that strong memory for them, because not only are they reading something in a textbook, but they're also assigning some procedural or kinesthetic memory. They're doing something with their hands, and that creates a really strong signal. And I wholeheartedly believe in this principle. At least from my own experience, my students that really that I expose these things to, they learn more than other places on campus that don't have access to my materials. And so, to that end, part of this is introducing things that can be scalable and accessible, because obviously, like, I can't give someone a bicycle wheel and a spinning chair. I can't give that to a classroom of people. I can't give an oscilloscope. And so, yeah, this is kind of the foundation of what I'm going to talk about. So, Embodied Games has worked on a lot of stuff over the past couple of years. We're working, I mean, we're still working on finishing some of our projects right now that I'm going to go over in this talk. But basically what I'm going to do is go over these games. I'm going to go over the science that underlies these games. I'm going to go over how we designed the games around the science, and then kind of talk about what we hope, or what we've found that students or people gain, or what we hope to find. And so this first game I'm going to talk about has to do with something called Batesian mimicry. Raise your hand or type in the chat if you've heard of this before. This is something that we see as a result of evolution. So excluding this butterfly in the middle in the top row, the first and the second row look very similar, don't they? And the second and third row look the third and fourth row look very similar as well. But the first and third are Batesian mimics, and what that means is that they've copied some evolutionary trait from another species in order for them to survive. So the second and fourth row butterflies are actually poisonous to birds, and the birds.
Sorry, we cannot see the slide.
Sorry.
It's stuck on slide 4. Okay, now.
There we go. Yep. Sorry.
Okay, now we are on butterflies.
Sorry, it's my first time on iLearn.
No
so these butterflies. I'll just recap real quick. The first and second row, okay, on the left and right. The first row is a Batesian mimic, and you can see they are very similar looking to the second row, and same goes for the third and fourth row. And the second and fourth rows of butterflies are poisonous to birds, and that is an evolutionary trait that they adapted to survive, right? But the first and third rows are not poisonous at all. All they did was evolve to look like the poisonous ones. Oh, man, this thing is finicky. All they did is look like the poisonous ones, and in doing so, they were naturally selected and are thriving, right? And this is a very interesting concept because it's basically it's basically a way for nature to evolve in a way that's not very intuitive. And so we made this game called Catch a Mimic, Natural Selection, which kind of played on this concept. And so we've got this is kind of how we prototyped the butterflies. At first, we kind of went a little more cartoony, but we decided after playtesting to go for a different design. And you can see, well, maybe it's a little hard to see on the right, the differences between the butterflies get less and less distinct. And basically, the player's role in this game is to catch butterflies for birds in your zoo, and you have to catch the correct ones. And it is pretty easy at first because it's noticeable which one is poisonous and which one isn't. But as Batesian mimicry happens, it becomes very, very difficult. And we have point system that ties to that concept. And all the while, like I said, we're doing the necessary 9. We're scaffolding the gestures. We're scaffolding the content. And so, this is available on desktop and VR on the Oculus Store. And so in VR, you have a net and you're catching the butterflies. And so that's that embodied gesture that helps you create that memory. And so this game, like I said, is available on the Oculus Store. And we did find that there was some learning gains happening for these students. And it should be known that, like, a theme for all of these games is that we had biologists as a biologist as a subject matter expert. We had a design team, like you said. There's different roles for people to play in the creation of games, as Andre's talk told us. And so this was a very interdisciplinary effort, much like the rest of our games. And we found that there was learning games, and this was a very successful project. And yeah, you can go ahead and play it on our website or on the Oculus Store. Now I'm going to move on to our next project, which was originally started as an Ebola outbreak modeler. And so we've got this equation here called the SIR model, which we used to create this augmented reality app that modeled the spread of Ebola. But during that work, the COVID-19 pandemic was starting, and so we kind of pivoted this effort to turn into a public health game, public health information game, and it turned into this COVID campus simulation. So in this game, a player will make some decisions throughout the day, and their probability of infecting other people or being infected goes up to a certain extent depending on what decisions you make. So wearing your mask below your nose versus not wearing a mask versus wearing a mask correctly, making decisions like that. And at the end, you have a probability of infection, and you can replay it as many times to get that probability as low as possible. And after every decision, there's some feedback. There's some reference on why that decision was good or bad. And we found with this game, actually, that there was a positive impact on players' health behaviors because we had a post-survey. And we also found that there was a higher confidence after playing the game in asking relevant questions related to a pandemic. And this is important because I don't think I need to tell anyone there's been a lot of controversy around the COVID-19 pandemic and what it means and what we should do and things like that. And so a game like this actually seemed to help that situation in a positive way. And I would urge people who are making games or interested in getting into this kind of work to use the real world as a jumping off point for creating something. It's funny. I don't think that sometimes I don't think it's as much a game as it is an experience, or it's just a thing to be a part of. And this is one of those things. It is a game, but it's also an important reminder for public health. And so moving on, there's this other game that we've been working on called Save the Building. It's all about tuned mass dampers. And here we've got some skyscrapers. It's the One Canada Square in London, the Tokyo Skytree in Tokyo, and the Taipei 101 in Taiwan. And these things are feats of engineering. I don't know if you've ever seen any of these in person. I've seen the Tokyo Skytree in person, and it's kind of majestic. These are great feats of human engineering, and you kind of wonder how things like this can stand, how these things can maintain safety and comfortability for the people inside, when they're subject to winds or earthquakes and things like that. And this is actually a major uh, topic in civil and industrial engineering, and that's what this game is kind of centered around. And it's actually part of a larger suite of experiences called the Career Arcade, which are designed to uh, gauge and increase interest in students who are undeclared or prospective students for the university, to see if they kind of like this sort of subject matter. And so in this game, we're talking about tuned mass dampers, and normally you see it like this in a textbook, right? Super immersive, right? There's some vibrating object, and basically you are creating something that can oppose that vibration. Because when things vibrate too much, they break or they creak or they sway a lot. And basically a tuned mass damper counteracts that by having something inside it or attached to it that can vibrate in the opposite fashion. And so this is a big topic in engineering, like I said, and it's very important work. But this may do the job, but wouldn't it be better if you could actually see one in action? And this is actually the Taipei 101 tuned mass damper, where whenever the building sways from wind or earthquakes, this big, however many times, I don't remember how heavy it is, it weighs a lot. It basically sways in response to keep the building straight and comfortable for everyone inside. And so we made a game mechanic based around this. And the game is called Save the Building. Like I said, it's for these undeclared freshmen and high school students. And in this game, you have the option to change 3 parameters, which in reality is actually what you're doing. Obviously, it's not as simple as this, but you can change the height of the pendulum, which, stemming from intro physics, that changes the frequency of the pendulum. There's the mass, which changes how much energy that pendulum can have. And then there's the stiffness of the pistons, which dampen that energy. And so a player will go through this game and set off earthquakes to see if their tuned mass damper worked. And so you can go up to a magnitude 6 earthquake with that joystick. Again, there's that embodiment. And you can see if your parameters were correct. And if they were, or if they weren't, the building breaks. And if they were, then the building is saved, and you've done a good job, and you have a bright future as a civil engineer. And again, there's that gesture, which maps to an earthquake, right? And in VR, we plan to have this kind of experience where you have the player in a helicopter going around the building. Oh, and by the way, I don't know if you saw, this thing on the bottom right is supposed to be an iPad. So it's like incorporating technology that you might end up using if you do end up out in the field as an engineer. They love their iPads out there. So this is the tuned mass damper building, and like I said, it's in this suite of experiences called the Career Arcade, related to construction. And here's another one. This would be on a tabletop in that room, where you can practice building a bridge. And you've got a certain budget. There's certain parameters. There's a terrain that you have to build the bridge over. This is earlier on in the prototyping process. But you can see that it's pretty nice. It could probably make someone interested in this sort of work. And again, it is important work. We need these bridge builders. We need these building makers, right? Because that's kind of what the world has come to at this point. And so these two experiences, in tandem with some other stuff that isn't specifically our lab is working on it, are being worked on for student interest. Now, I've got another cool project here. We don't have a name for it yet. This is also in the prototyping phase, but it's based around this idea of chemical titration. Now, titration is this chemical technique where you have something that's either acidic or basic, and you want to neutralize it. And so you add very, very specific quantities of the opposite of whatever is in your solution, in your flask, in order to neutralize it. So if you've got something very acidic in this bottom beaker right here, you will take what's called a titrant and add very limited, yeah, it's painful to do for me to call, yeah. You add a very controlled amount of liquid of something that's the opposite. So if there's something acidic, you're adding very specific quantities of something basic until you get that equivalence point, that pH of 7. And again, when we talk about scalable experiences, I mean, this is a beaker, it's this stopcock, it's this tube, it's the solution, and that's just for one student or one lab group, and that can be a tall ask for some people, especially in more underprivileged communities. And so we wanted to make it. We want to make an experience around this, and this is more. This isn't a virtual or augmented reality experience. It's actually a mixed reality experience. So what we've got here is, in conjunction with Meteor Studio, which is another XR group at ASU, we made this. There's this fluid simulation, so it's realistic fluid effects in the virtual environment, but the stopcock is actually mapped to a controller on the outside, which we've 3D printed to look and feel like a titration setup. And so we've got this, and this stopcock maps directly to the stopcock in the game. And so users will, at least what we hypothesize is that the equivalent learning gain should be equivalent because they're doing the same thing as they would in a real lab with fluid and a tube and a titrant and the same kind of chemical procedure. But what we get from this is that it's cheaper, right? This 3D printed plastic and little controller board here, I think, costs less than $10, right? And you get unlimited trials. Like if you mess up the solution, you don't have to clean everything and reset. And you also can do it as many times as you want with this. And we want to eventually build this out to be part of a distance learning curriculum, for example. We can easily send out, or we can easily send out a set of these, or people can print them on their own, right? Or build them on their own. I mean, it's not a terribly difficult schematic once the program is more fleshed out. And so this is a very exciting thing that we've been working on. Our pilot study just started on this, and so far is looking positive from the few students that we've had. And so, yeah, this is definitely something to look forward to. Now, speaking of these physical sciences, one second, I'm going to drink water. I'm going to move on to something very near and dear to my heart. I'm the physicist, right? So there's this other project that was worked on, and I'm currently running study participants on the usability of, called MAGNA-AR. And the whole thing is that we want to visualize the invisible. So this is a NSF grant. It's the National Science Foundation in the U.S. It's an NSF grant that looked at using current technologies to enhance the future of STEM education and its implications for the future workforce. And so we realized, working with a software team called Viera Software, that phone sensors have all these great physics or physical measuring tools, right? There's the accelerometer, which can measure a g-force. There's inclinometers. There's magnetometers. There's a compass. There's a light meter, light sensors, all sorts of things. And these are directly accessible through your phone. And if they're accessible through your phone, they're accessible for an app, right? And that's kind of the starting off point for this project, which was, hey, everyone's got phones, and everyone, at least in the education realm, needs equipment. Why not just use the phones as the equipment? And this is a beautiful thing because it really works to a high degree of precision. And so we went a little further, combining this magnetometer and the accelerometer, and doing what you would call odometry. And we kind of in this app called MAGNA-AR, which can overlay an accurate magnitude and directionality of magnetic fields in augmented reality in real time. So there's always like an ambient magnetic field on Earth, right? You can download this app and find out what that is at that point in space and time where you are. So you could even download this now. It's free on the Google and Apple stores. And basically what we wanted to get at was, how do people learn about magnetic fields? This is a very fundamental STEM concept, right? This is something that, I mean, everyone in STEM, whether you're pre-med or engineering or anything really, you have to take physics, and this is one of the most fundamental things you can know, how a magnetic field works from a dipole. And so this is a nice drawing. It's two-dimensional. It's cool. I mean, it gets the point across, I guess, but in reality, the magnetic fields are 3 dimensions. You have to rotate this to get a full picture, and you can't really do that on a 2D screen. You can't really do that in real life either. So, like I said, I'm a physics educator. This is what I would do in real life to kind of demonstrate that concept, right? This kind of looping magnetic field. And these are iron filings on the left, which respond to the directionality of the field. And then also there's a bunch of compasses, little tiny compasses around that other one that kind of do the same thing. And in both of these, I think they're great images, but they are kind of difficult to look at. They're difficult to scale. I can't just get iron filings somewhere, right? Like, that's a very niche thing. And in the right picture here, there's 80 compasses to get this point across, and those compasses can become demagnetized, or you can lose them because they're very small, or things like that. And then on top of that, like I said, this is still two-dimensional, so it's not even a complete picture. But this is how we've been doing it for a very long time. And to kind of hammer home the importance of this bar magnet, this dipole magnet, Earth's magnetic field is actually very well modeled by the dipole magnet mathematics. And so this kind of looping from north to south, the magnetic north to magnetic south, which is actually the opposite of geographic north and south. This is the way the magnetic field on Earth behaves at this point in time. And you can use the app, again, to find this ambient field wherever you are in the world. And I encourage you to do that, because we did that with students in different parts of the world. And what did they find, right? So I want you to, I'll go back to this picture, but try to remember, in the south here, the magnetic field is pointing outward from the ground. It's pointing kind of inclined up. And above the magnetic equator, it's pointing downward, right? And so remember that. And actually remember that if you're going to download the app and do it yourself, because what we found with these students was that when you're in Stockholm, Sweden, like I said, it's very far inclined or declined to the ground, right? Because that's in the northern hemisphere. So look at that picture. In the northern hemisphere, it's very declined. In Lima, Peru, near the equator, it's almost horizontal, right? We had students do that there. And in Sydney, Australia, that's the southern hemisphere. It's pointing upward. And so we have, all of a sudden, through this really accessible smartphone app, we've gotten international collaboration between students to verify geologically sound findings. And that's a beautiful thing, right? and everyone has the agency to do it from their own phone. Well, not every phone. There is a little bit of a barrier in terms of what's AR enabled at this point. So anything beyond like an iPhone 8 or an Android. I forget the model for the Samsung line of phones, but basically this is very accessible, and you can do some real science with it. And in addition to that, because it's your phone, you can kind of probe your own environment, right? And so what I did, because I'm a physicist, I know that speakers have some coils in them. I wanted to see if this thing could map the magnetic field in the speakers. And so I turned on the speaker, I turned on the app, and lo and behold, you get this great solenoid magnetic field that's color coded by strength, and it has the correct dimensionality and everything. And this is I thought this was really cool. I had never seen anything like this before, and this is kind of a first of its kind sort of application. And here's another thing with a soundbar. Did you know soundbars have two speakers in them? Because that's what this picture says. And I didn't know that until I went and did it for myself. And so there's this. Marcos asks, how is the visualization done? So the magnetometer and the phones basically have these things called Hall sensors that measure very tiny electric currents due to magnets, and that current is turned into a voltage that it reads. And it does this for the X, Y, and Z axes. And you combine that knowledge with the AR capabilities, where it can detect planes and objects in your space, and you combine that with the accelerometer of the phone, so the phone knows how fast it's moving, how it's rotating, and all of that combined in conjunction with each other leads to this. Yeah, we can talk about it a little more after. Now, I do have a little time left. I didn't know if I was going to go over or under at this point. And so that's about it for the embodied game stuff, but there is one more project that I'm very excited about that is more just a broader ASU thing called Dreamscape Learn, which is this partnership between Dreamscape Immersive, which is a virtual reality amusement company, Arizona State, and Verizon. And basically, it's this fleshed out world with fully rigged, hand-tracked avatars with inverse kinematics and all that stuff, where students can be explorers in this alien zoo, and they learn biology that way. And we're actually running this pilot study right now. It's very, very high budget. This is the artwork for it. It's almost, in this experience, it's almost like a AAA quality level of animations and voiceovers and storytelling. So Dreamscape Immersive is actually born from Walter Parks and a collaboration between Walter Parks, who made Gladiator and Men in Black, among other movies, and Steven Spielberg. They combined their storytelling expertise with some technical people, Cecilia Charbonnier, and they made these experiences. And the president of our university kind of said, "Wow, this is a super immersive, super interactive environment. We should be able to adapt this for education, and I think it'll transform education." And so we have our instructional and curriculum design people at ASU, along with the learning science research people, which that's the group that I'm a part of, and we're kind of fleshing out the modules to be available to students right now. And the Alien Zoo is the first one, where they're learning about the food web. Now, I in particular am going to be looking at user movement data, so the X, Y, Z, and roll, pitch, yaw, the rotation of everyone's hands and head, so where they're looking, what they're pushing and interacting with, at a sample rate of 10 hertz. And so every tenth of a second, we know what they're doing. And I'm going to be looking at this data, looking to see what people are paying attention to, what's making them motion sick, if anything. Are we directing their attention correctly? is this attention related to learning gains, right? These are all interesting questions that we can ask. And like I said, this data collection on this experiment and this experience just started last week, so that data is still coming in, and it's a very exciting thing to be a part of. And this data will inform future design decisions of experiences using the same kind of dreamscape framework. And so just to recap, we went over all of these experiences here. Catch a Mimic, COVID Campus, Save the Building, Chemical Titration, Building the Bridge, MAGNA-AR, and the Dreamscape Learn experience all have some things in common. And these are the things that I want you to take away if you're thinking about how immersive tech can be in STEM education. First and foremost, the real world is very inspiring. Like the study of physics or chemistry or biology is nothing short of beautiful. There's a lot of things, even if you're not going to make an educational game, there's a lot of things in nature, just actual physical natural phenomena, that serve well as game mechanics or jumping off points for story, right? And we see this in a lot of different games. So I encourage you, if you're a game designer, look at some cool thing, like watch a documentary, a nature documentary, or watch a physics documentary, right? Like I find myself as I've come into my own as a Unity developer, that the mathematics is already there and you just code it, and all of a sudden you can replicate it and do something really cool. The second takeaway is that designing these experiences for STEM ed is very interdisciplinary. Like I said, there's artists and coders, but there's subject matter experts and learning researchers, and they've all got to work together. And it's a lot of work, but when it's done correctly, it can result in something really meaningful and really impactful for people. I gotta bring up the necessary 9 again. Embodiment plus immersion is super important with these immersive experiences. So the level at which we can replicate true to life gestures and like real kinesthetic sense for people really plays a big role in how immersed they are in the world and what they're learning. And then the last point is that some of the immersive tech can be scalable. Now, I'm not going to say that everyone can just go get a VR headset, because we're not there yet. But in terms of what you can do with AR and the kind of prevalence of AR-enabled devices as it stands right now, that's definitely something that you can work on. And it's something easy to get into and something that can impact a lot of people. And so... yeah, that's about it for me. I don't have a outro slide or anything, but I hope you enjoyed this talk, and let's do some Q&A.